3 years ago, I was struggling with a recommendation engine that took hours to train on even modest datasets. Then I discovered how to properly implement SVD within my machine learning pipeline. Processing time dropped by 92%. Today, I'm showing you exactly how SVD fits into the broader machine learning ecosystem, not just what it is, but where and how to use it strategically. Whether you're building recommender systems or processing image data, this systems approach will change how you think about dimensionality reduction. What if I told you the biggest challenge in modern machine learning isn't algorithms or computing power, but something far more fundamental? As our datasets grow larger and more complex, we're facing what experts call the curse of dimensionality, a phenomenon that silently undermines even the most sophisticated machine learning systems. Think about what happens when you collect data in the real world. A simple grayscale image at just 256 pixels translates to 65,536 dimensions, one for each pixel. A text document using a standard vocabulary creates a feature space with tens of thousands of dimensions. These aren't exceptional cases, they're everyday scenarios in modern machine learning. The problem is that as dimensions increase, the volume of the space expands exponentially. Imagine a cube in 3D space. Now imagine that same cube in 100 dimensions. The volume becomes so vast that data points, no matter how numerous, become incredibly sparse. This sparsity creates a fundamental challenge for machine learning algorithms that depend on finding patterns in dense data distributions. What makes this particularly troubling is how traditional distance metrics break down in high dimensions. In a 2D plot, you can easily see clusters and patterns. Points that are close together are meaningfully similar, but something strange happens as dimensions increase. This intuitive relationship starts to fail. Let me explain this with a simple example. In low dimensions, calculating the Euclidean distance between 2 points gives us a meaningful measure of their similarity. But in high-dimensional spaces, a phenomenon occurs where the distance between any two random points tends to become nearly the same. This convergence of distances means algorithms struggle to distinguish between what's similar and what's different. The very foundation of pattern recognition collapses. The computational burden explodes as well. Consider a common algorithm like k nearest neighbors, KNN. Its time complexity increases linearly with the number of dimensions. What works efficiently in 10 dimensions becomes painfully slow in 10,000 dimensions. Resources that were once abundant suddenly become scarce, creating bottlenecks that can bring entire machine learning pipelines to a crawl. But here's the true paradox of dimensionality. While having more features theoretically provides more information, it often leads to a dramatic decrease in the signal-to-noise ratio. As dimensions grow, the useful signal in your data gets buried under an avalanche of noise. Algorithms struggle to separate meaningful patterns from random fluctuations, leading to overfitting and poor generalization, especially evident in text processing when using approaches like bag of words. We can visualize this in a machine learning pipeline. Raw data enters the system with thousands or millions of dimensions. It travels through pre-processing, feature extraction, and model training. But at each stage, the high dimensionality creates congestion points where computational resources are strained and algorithmic effectiveness diminishes. The pipeline that should flow smoothly instead becomes clogged with redundant, noisy, and computationally expensive dimensions. In natural language processing, this manifests when texts are converted to numerical representations. What starts as meaningful sentences becomes sparse vectors in a vast feature space where traditional algorithms struggle to find coherent patterns. The same problem appears in computer vision, where the pixel-by-pixel representation creates unnecessarily complex models that capture noise rather than underlying structures. What's particularly troubling is how this affects visualization and human understanding. Our brains excel at recognizing patterns in 2 or 3 dimensions, but we're completely unable to conceptualize what happens in 1,000-dimensional spaces. The very tools we use to understand data fail us when dimensions explode. This isn't just a theoretical problem. It creates very real bottlenecks in production systems. Models become unnecessarily complex, training times extend from minutes to days, and inference speed grinds to a halt. Storage requirements balloon, and the interpretability of results diminishes dramatically. So what's the solution to this fundamental challenge? We need systematic approaches to reduce dimensions while preserving the essential information in our data. This is where dimensionality reduction techniques, particularly singular value decomposition, SVD, become critical. SVD acts as a bridge between unwieldy high-dimensional data and efficient, effective machine learning models by identifying and preserving only the most informative dimensions. Dimensionality reduction bridges the gap between raw data and effective models, but this bridge isn't suspended in isolation. In the architecture of machine learning systems, data flows through multiple transformations before it becomes useful, yet many practitioners treat these pre-processing stages as mere technical details rather than the critical foundation they truly are. To truly understand SVD's role, we need to map out the entire machine learning landscape and see where dimensionality reduction creates its greatest impact. Imagine a comprehensive systems view of the machine learning ecosystem, not just isolated algorithms, but the entire workflow from raw data to actionable insights. At the highest level, machine learning architectures follow a consistent pattern. Raw, unstructured data enters the system and must navigate through a series of transformations before it can power useful models. The pre-processing phase, often overlooked in favor of more glamorous model architectures, is where some of the most consequential work happens. This pre-processing stage includes critical operations like data cleaning to handle missing values and outliers, normalization to bring different features into comparable scales, and transformation to convert categorical variables into numerical representations. These steps create the foundation for everything that follows, yet they're frequently treated as routine plumbing rather than strategic decisions. Within this pre-processing ecosystem, dimensionality reduction techniques like SVD occupy a pivotal position. They serve as the crucial intermediate step between raw high-dimensional data and the refined input that machine learning models require. This position makes them disproportionately influential on the entire system's performance. Consider how different machine learning domains implement this architectural pattern. In computer vision pipelines, raw pixel data from images needs extensive transformation before neural networks can effectively process it. SVD plays a key role here, enabling image compression and feature extraction that makes subsequent processing more efficient. Rather than feeding thousands of raw pixel values into a model, SVD can extract the essential visual patterns that distinguish one image from another. Similarly, in natural language processing, text documents initially exist in an extremely high-dimensional space where each potential word represents a dimension. Before this text data can be effectively modeled, it must be transformed into a more compact representation that captures semantic relationships. SVD provides the mathematical machinery for techniques like topic modeling and semantic analysis, revealing the underlying structure in language data. What's fascinating is that across these diverse domains, from image recognition to text analysis to recommender systems, we see the same fundamental pattern. High-dimensional data must be transformed into more manageable representations before effective modeling can occur. This isn't merely a convenience, it's a mathematical necessity driven by the fundamental challenges of high-dimensional spaces. Most system diagrams of machine learning pipelines show a simplified flow. Data in, model training, predictions out. But this conceals a critical black box where dimensionality reduction occurs. Opening this black box reveals a sophisticated process that's less about eliminating information and more about distilling it to its most valuable essence. Think of SVD as performing a type of universal translation service within this system. It takes the raw, unwieldy language of high-dimensional data and translates it into a more compact, structured form that machine learning algorithms can effectively process. This translation preserves the most informative aspects of the data while discarding noise and redundancy. What makes SVD particularly valuable in this landscape is its versatility. Unlike specialized techniques that work only for specific data types or applications, SVD provides a mathematical foundation that can be applied across different domains and data structures. It represents a unifying principle in the otherwise fragmented world of machine learning techniques. By mapping the machine learning landscape this way, we can see that SVD doesn't just solve an isolated technical problem. It addresses a fundamental architectural challenge in building effective machine learning systems. It creates the critical bridge between the messy, high-dimensional world of raw data and the structured inputs that machine learning models require to function effectively. Imagine being able to take any matrix, regardless of its size, shape, or complexity, and decompose it into three simpler matrices that reveal its fundamental structure, like an X-ray reveals a skeleton. This mathematical superpower exists, and it's called Singular Value Decomposition, or SVD. Behind the scenes of every dimensionality reduction operation lies a fundamental mathematical question. How can we break down complex data structures into simpler, more manageable components? Matrix factorization provides the answer by splitting matrices into products of other matrices with specific properties, but not all factorizations are created equal. The challenge that mathematicians and computer scientists faced was finding a universal decomposition that would work for any matrix, square or rectangular, invertible or not, well-conditioned or nearly singular. Many matrix factorizations like LU or Cholesky decomposition come with restrictions, working only for square matrices, or requiring specific properties like positive definiteness. SVD breaks through these limitations with an elegant solution. At its core, SVD states that any matrix X can be decomposed into three specific matrices. X equals U times sigma times V transpose. This seemingly simple equation unlocks profound insights into data structure. Each component of this equation plays a distinct role in the decomposition. The matrix U contains what we call the left singular vectors, which represent the directions of maximum variance in the output space. Think of these as the fundamental patterns that emerge when our data is transformed. These vectors are orthogonal to each other, meaning they represent completely independent directions in the data space. The diagonal matrix, sigma, contains the singular values arranged in descending order. These values indicate the importance of each direction identified by the singular vectors. Larger values correspond to directions that capture more variance in the data, essentially telling us which patterns matter most. When we examine these singular values, we're looking at the intrinsic dimensionality of our data, revealing how many meaningful components we actually need to represent it. The matrix V transpose contains the right singular vectors, which reveal the relationships between the original features in our data. These vectors help us understand how different variables interact to create the patterns we observe. Like U, these vectors are orthogonal, providing a set of independent directions in the input space. Geometrically, we can interpret SVD as a sequence of transformations that reveals the true nature of our data. First, V transpose rotates the data points into a new coordinate system. Then, sigma scales these rotated points along each axis according to the singular values. Finally, U performs another rotation to complete the transformation. This sequence aligns the axis of our data with the directions of maximum variance, creating a coordinate system that reflects the natural structure of the information. What makes this geometric interpretation so powerful is that it helps us visualize how SVD can compress data while preserving its essential characteristics. The square of each singular value tells us precisely how much variance is explained by its corresponding direction. This direct relationship between singular values and variance makes SVD an unparalleled tool for understanding data structure. To help visualize this concept, think of SVD as similar to image compression. When we apply SVD to an image represented as a matrix of pixel values, we can approximate it using only the largest singular values and their corresponding vectors. This rank reduction captures the most important features while effectively filtering out noise, a mathematical form of signal processing that works on any type of data matrix. The Eckart-Young theorem provides the mathematical guarantee behind this approach, stating that the best rank R approximation of a matrix in terms of minimizing the Frobenius norm, a measure of matrix difference, comes from the truncated SVD, where only the top R singular values are kept. One particularly elegant aspect of SVD is that the unitary nature of matrices U and V ensures that the transformations preserve angles and distances between vectors. This property maintains the geometric relationships within our data during decomposition, ensuring that similar data points remain similar even in the transform space. What's remarkable about SVD is how it reveals this hidden structure without making assumptions about the data. It doesn't care if your matrix represents images, text, sensor readings, or financial transactions. SVD extracts the fundamental patterns regardless of the domain. Ever wondered what it actually looks like when your high-dimensional data gets decomposed into its fundamental components? While the mathematical formulation of SVD is elegant, the true power of this technique becomes dramatically more intuitive when we can visualize its transformations. Let's bring SVD to life with a simple 2D dataset. Imagine a cloud of data points scattered across a plane, but not randomly. They form an elongated elliptical pattern. This natural directional spread isn't accidental. It represents the inherent structure of our data. When SVD works its magic on this data set, it follows a three-step geometric transformation that we can actually watch unfold. The first step involves discovering the directions of maximum variance in our data. If you look closely at our scatter plot, you might intuitively spot these directions. They're the axes along which our data stretches the furthest. What SVD does is mathematically identify these principal directions, which correspond to the right singular vectors. Visualize this as a rotation of our original coordinate system, where the new axes perfectly align with the natural spread of our data points. What's fascinating is that SVD finds these optimal directions without making any assumptions about what our data represents. It simply follows the mathematical structure. Now comes the second transformation, projection and scaling. Once SVD has identified these optimal directions, it projects our data points onto this new coordinate system. But SVD doesn't just rotate, it also scales the data along each new axis according to the singular values. This scaling effect can be visualized as a compression or stretching of our data cloud along each of the new directions. The largest singular value corresponds to the direction with the most variance, causing the greatest stretching in that dimension. Meanwhile, directions with smaller singular values undergo more compression. The third step reveals the true power of SVD as a dimensionality reduction technique. Here, we can reconstruct an approximation of our original dataset using only the top singular values and their corresponding vectors. In our 2D example, we might decide to keep just the direction with the largest singular value. This reconstruction process creates a simplified version of our data that captures its essential structure. Visually, this appears as a projection of all data points onto the principal direction. essentially reducing our 2D dataset to a line. What's remarkable is how much of the original pattern this simplified representation preserves. The real magic happens when we extend this visualization to higher dimensions. While we can easily see what's happening in 2D, SVD works identically in spaces with hundreds or thousands of dimensions. By projecting high-dimensional data onto the first 2 or 3 singular vectors, we can create a visual window into otherwise imperceptible patterns. Imagine we have a dataset with hundreds of dimensions. When we apply SVD and visualize the projection onto just the first 2 singular vectors, previously hidden clusters and relationships suddenly become visible. This is how SVD serves as our dimensional periscope, allowing us to peek into the structure of complex data. The relationship between singular values and data variance becomes particularly illuminating when visualized. If we plot these values against their indices, we typically see a rapid drop-off. A few large singular values followed by many smaller ones. This visual tells us that most of the information in our dataset is contained in just a few dimensions, which is precisely why dimensionality reduction works. Animated visualizations make this even clearer, showing the sequential transformations as data undergoes rotation, scaling, and projection. These dynamic representations reveal SVD as a geometric dance, where data points move in concert to reveal their underlying structure. Perhaps most importantly, these visualizations help us understand why SVD is so effective at separating signal from noise. The directions corresponding to larger singular values capture meaningful patterns, while those with smaller values often represent noise. By keeping only the top components, SVD naturally filters out the noise, resulting in a cleaner representation of our data. In the expanding universe of dimensionality reduction methods, SVD continues to stand out despite numerous newer alternatives promising improved results. Why does this mathematical approach remain the benchmark against which all other techniques are measured? The answer lies in a fundamental property that makes SVD uniquely powerful. It serves as the mathematical foundation that connects seemingly different reduction methods to the same core principles. The modern data scientist faces a bewildering array of dimensionality reduction options. Each technique comes with its own mathematical foundation, computational requirements, and visualization properties. This creates a significant challenge. How do you select the right approach for your specific dataset and analytical goals? The decision isn't merely academic. Choosing inappropriately can lead to misleading interpretations or computational inefficiency that undermines your entire analysis pipeline. The relationship between SVD and principal component analysis illustrates why SVD maintains its central position in data science. While often treated as separate techniques, PCA can actually be derived directly from SVD. When you compute the principal components as eigenvectors of the covariance matrix, you're essentially performing a calculation that SVD can accomplish more directly. This mathematical connection isn't just an interesting footnote, it demonstrates how SVD provides the underlying framework that powers other popular techniques. Where SVD truly distinguishes itself is in its approach to data structure. Unlike techniques like TSNE and UMAP, SVD captures global patterns in your dataset. This global perspective is crucial when you need to understand the overall structure of your data rather than just local relationships. TSNE and UMAP excel at preserving local structures, making them excellent for visualization tasks where nearby points matter more than distant relationships. However, this local focus comes at a cost. They can sometimes distort the global picture, leading to misleading interpretations if you're not careful. Consider what happens when you apply these different techniques to the same data set. SVD will faithfully represent the major directions of variance across your entire dataset, while TSNE might create visually appealing clusters that don't necessarily reflect the true global structure. Neither approach is inherently superior. They simply prioritize different aspects of your data. This distinction explains why many data scientists use SVD as their starting point before exploring more specialized techniques. For datasets with specific constraints, techniques like non-negative matrix factorization, NMF, offer targeted advantages. NMF is particularly valuable when working with non-negative data, such as image pixels or text document frequencies. Its constraint that all factors must be non-negative often produces more interpretable components for these data types. However, this specialization comes with a trade-off. NMF lacks the global structure preservation that makes SVD so broadly applicable across different domains. Computational efficiency becomes increasingly important as datasets grow larger. This is another area where SVD demonstrates its value. Benchmark results consistently show that SVD implementations in optimized libraries scale effectively to large datasets, often outperforming other techniques in terms of speed. While exact SVD computation can be intensive for extremely large matrices, approximation methods allow it to scale to massive datasets without sacrificing essential accuracy. The decision about which dimensionality reduction technique to employ ultimately depends on your specific analytical goals and dataset characteristics. For exploratory data analysis where visualization clarity is paramount, TSNE or UMAP might be preferable despite their computational intensity. For building robust machine learning pipelines where computational efficiency and mathematical stability matter more, SVD offers significant advantages. When working with non-negative data where interpretability is critical, NMF provides specialized benefits that other techniques can't match. Beyond the choice between SVD and other reduction techniques lies a surprising revelation that many data scientists overlook. PCA, arguably the most popular dimensionality reduction method taught in virtually every machine learning course, is mathematically just SVD wearing different clothes. This connection isn't immediately obvious because these techniques are typically introduced as separate approaches. Principal component analysis has become the go-to method for exploratory data analysis and pre-processing across countless disciplines. From genetics to finance, PCA helps scientists identify the primary patterns of variation in their data. But beneath this widespread application lies a mathematical relationship that transforms how we understand dimensionality reduction. When we perform PCA, what we're actually computing are the eigenvectors of the covariance matrix of our centered data. These eigenvectors represent the directions of maximum variance, the principal components we're seeking. The process starts by centering the data, subtracting the mean from each feature, then calculating the covariance matrix that captures how variables change together. Finally, we extract the eigenvectors and eigenvalues from this covariance matrix. Here's where the connection emerges. When you apply SVD to centered data, something remarkable happens. The right singular vectors in matrix FIV correspond exactly to the eigenvectors of the covariance matrix. Furthermore, the singular values in the diagonal matrix S are directly related to those eigenvalues. They're simply the square roots of the eigenvalues of the covariance matrix. Let's trace this step by step. When implementing PCA from scratch, you would 1. Center your data matrix by subtracting the column means. 2. Compute the covariance matrix. 3. Find the eigen decomposition of this covariance matrix. 4. Sort the eigenvectors by their corresponding eigenvalues. 5. Project your data onto these eigenvectors to get the principal components. Alternatively, using SVD, you would 1. Center your data matrix. 2. Apply SVD to this centered matrix to obtain U, sigma, and V3. The columns of V are already your principal components. The values in sigma squared directly correspond to the eigenvalues. The equivalence becomes apparent when working with the same dataset. Both approaches yield identical results when the data is properly centered. This isn't just a mathematical curiosity, it has practical implications for implementation. SVD can often be computed more efficiently than explicitly forming the covariance matrix, especially with large datasets where direct eigendecomposition becomes computationally intensive. Where these methods diverge is when working with non-centered data. PCA specifically requires centering as part of its definition since we're looking for directions of maximum variance relative to the mean. SVD, however, can be applied to any matrix regardless of centering. This makes SVD the more general technique, with PCA emerging as a special case under specific conditions. This relationship becomes particularly important when implementing dimensionality reduction in practice. Many modern libraries implement PCA using SVD behind the scenes precisely because of this mathematical equivalence. The SVD approach often provides better numerical stability and performance, particularly for large datasets. The Eckhart-Young theorem further cements this connection by proving that the best rank R approximation of a matrix can be achieved using the truncated SVD. This directly aligns with PCA's goal of finding the R directions that capture the most variance in the data. Visualization of this relationship reveals that when we plot data using the first few principal components from PCA, we're effectively plotting the same transformation we would get from projecting onto the first few right singular vectors from SVD. The points appear in identical positions, confirming the mathematical equivalence. The mathematical equivalence between PCA and SVD is elegant in theory, but the implementation decisions you make can lead to performance differences of up to 100x in real-world applications. What separates an SVD implementation that crawls from one that flies isn't just about the algorithm, it's about the ecosystem of choices surrounding it. Let's look at how SVD actually integrates into a production machine learning pipeline. In most workflows, after initial data collection and cleaning, you'll encounter a pre-processing stage where dimensionality reduction becomes critical. This is precisely where SVD enters the picture, bridging raw data and model training. When implementing SVD in Python, you have several options at your disposal. Using NumPy, the implementation is straightforward with just a single line of code: usvt_s_nep linealg.svdx. This gives you the complete decomposition with U containing the left singular vectors, S containing the singular values, and VT containing the right singular vectors. But simplicity doesn't always mean optimal performance. For larger datasets, scikit-learn offers a more specialized approach through sklearn.decomposition, truncated SVD. This implementation is particularly efficient because it only computes the top k components you specify rather than the full decomposition. The difference in execution time can be dramatic when working with high-dimensional data, where you might only need a small fraction of the singular values. But before applying any SVD implementation, proper data pre-processing becomes absolutely crucial. One of the most common pitfalls is neglecting this step. SVD is highly sensitive to the relative scales of your input features. Without proper scaling, features with larger numerical ranges will dominate the decomposition, essentially drowning out the information in smaller scale features. The pre-processing checklist should include scaling your data to ensure all features contribute equally. This might involve standardization, subtracting the mean and dividing by standard deviation, or normalization, scaling to a fixed range like 0 to 1. Centering the data by subtracting the mean is particularly important when you're using SVD for tasks similar to PCA. Another critical pre-processing consideration is handling missing values. In real-world datasets, gaps in the data can severely distort SVD results. Techniques like imputation, replacing missing values with estimates, must be applied before decomposition to avoid skewed outcomes. Once you've computed your SVD components, integrating them into the downstream pipeline requires careful design. A structured approach involves creating pipeline objects that connect your dimensionality reduction step directly to your modeling stage. This ensures consistency between how data is processed during training and inference. For example, after applying SVD to reduce dimensionality, the transformed data can flow seamlessly into classification or regression models. This integration not only enhances model performance by reducing noise, but also decreases computational load during both training and inference stages. In recommender systems and image processing applications, this pipeline structure becomes particularly valuable. Performance benchmarking reveals significant efficiency gains from proper SVD implementation. The randomized SVD approach has demonstrated speed improvements of up to 100 times compared to traditional methods while maintaining comparable accuracy. This becomes especially important when dealing with large-scale data that pushes memory limits. For extremely large datasets that exceed available memory, the method of snapshots provides an elegant solution. This approach processes data in manageable chunks to compute the SVD without requiring the entire dataset to be loaded simultaneously. This technique has found particular success in fields like fluid mechanics, where massive datasets are common. Beyond speed, your implementation choices directly impact model accuracy, interpretability, and deployment feasibility. Each decision creates ripple effects throughout the entire machine learning system. The wrong implementation approach can bottleneck your entire pipeline, regardless of how sophisticated your models are. While implementation choices determine pipeline efficiency, the most fundamental SVD decision happens earlier, when you determine exactly how many dimensions to retain in your decomposition. This seemingly simple decision marks the precise boundary between signal and noise in your data. Choose too conservatively, and you'll discard valuable information. Be too generous, and you'll preserve meaningless noise that degrades model performance. The truncation problem represents a delicate balancing act. Every singular value you retain adds computational complexity to your pipeline, but potentially increases the fidelity of your representation. The question becomes, at what point does additional fidelity stop representing actual signal and start preserving random fluctuations? Traditional approaches to this problem have relied heavily on rules of thumb and visual inspection. The elbow method involves plotting singular values in descending order and looking for a sharp drop-off, a bend in the curve where the contribution of additional dimensions diminishes rapidly. While intuitive, this approach introduces subjectivity. What looks like an obvious elbow to one analyst might appear gradual to another. Another common approach sets percentage thresholds, typically retaining enough singular values to explain 90% or 95% of the total variance. This method provides more consistency, but applies the same threshold regardless of dataset characteristics. A 95% threshold might be perfectly appropriate for clean, well-structured data, but insufficient for datasets with complex hierarchical patterns. Fixed dimension thresholds represent the simplest but least adaptive approach, keeping a predetermined number of singular values regardless of the underlying data structure. While computationally predictable, this approach disregards the actual information distribution in your specific dataset. What if we could move beyond these heuristics to a more rigorous, statistically grounded approach? This is where the Gavish-Donohoe optimal hard threshold method enters the picture. Rather than relying on arbitrary cutoffs, this method establishes a systematic approach by identifying a noise floor based on the singular values of a noise matrix. The method works by determining which singular values exceed what would be expected from pure noise. By analyzing the distribution of singular values, Gavish-Donohoe identifies the first singular value that rises significantly above the noise threshold, effectively drawing a statistically valid line between signal and random fluctuations. This approach is particularly powerful for matrices corrupted by noise, where the boundary between meaningful patterns and random variation becomes blurred. In experimental comparisons, the difference between optimal and suboptimal truncation can be dramatic. A recommender system using the standard 95% variance threshold might retain dozens of unnecessary dimensions, increasing computational load while actually reducing recommendation accuracy by 12 to 15% compared to the statistically optimal threshold. Image reconstruction tasks show similar patterns. Optimal truncation not only processes faster, but produces visually superior results by excluding noise dimensions. The computational impact of truncation cannot be overstated. Each additional dimension retained creates ripple effects throughout your pipeline. A facial recognition system truncated using Gavish-Donohoe showed 40% faster processing time while maintaining equivalent accuracy compared to a system using the 95% variance rule. In large-scale text analysis, optimal truncation reduced memory requirements by over 60% while improving classification performance. Beyond the mathematical formulation, truncation decisions should consider system resources and application requirements. A real-time recommendation engine might prioritize lower dimensionality to meet strict latency requirements, while a medical imaging application might retain additional dimensions where the cost of missing subtle patterns outweighs performance concerns. This suggests the need for a more nuanced, context-aware decision framework. Rather than applying a single threshold across all scenarios, optimal truncation should incorporate 1. Noise characteristics of the specific dataset. Statistical significance thresholds appropriate to the domain. 3. Available computational resources. 4. End application tolerance for false positives versus false negatives. 5. Interpretability requirements of downstream models. In practice, a hybrid approach often yields the best results. Begin with statistical methods like Gavish-Donohoe to establish a baseline, then adjust based on application-specific requirements and performance validation on held-out data. Modern pipeline architectures can even incorporate adaptive truncation, where the threshold adjusts automatically based on ongoing performance metrics. Even the most sophisticated truncation techniques assume you have complete data to work with. But what if half your matrix is empty? Imagine trying to reconstruct a partially destroyed photograph when only random pixels remain visible. This scenario isn't just a theoretical exercise, but represents the reality of many real-world datasets. In practice, pristine datasets are the exception rather than the rule. Machine learning practitioners regularly face matrices riddled with missing values, corrupted entries, or significant noise. These imperfections arise from sensor malfunctions, human error in data collection, privacy-preserving data masking, or simply the inherent sparsity of certain data types. Traditional SVD algorithms break down when confronted with these challenges. They simply cannot process matrices with unknown entries. This is where matrix completion techniques based on SVD reveal their transformative power. These approaches can fill in missing values by leveraging the correlations and patterns present in the observed entries. The fundamental insight driving these methods is that if your underlying data has a low-rank structure, meaning it can be represented efficiently in fewer dimensions, then you can recover the complete matrix even when a substantial portion is missing. The Netflix prize competition dramatically illustrated this capability. Contestants faced a massive user item matrix, where each user had rated less than 1% of available movies. Standard SVD couldn't be applied directly, but matrix completion techniques allowed teams to predict the missing ratings with remarkable accuracy. These methods work by iteratively estimating the missing values while simultaneously computing a low-rank approximation of the resulting complete matrix. But what about data that isn't just incomplete, but actively corrupted. This is where robust PCA approaches come into play. While standard PCA, and by extension SVD, is highly sensitive to outliers and corrupted values, robust PCA decomposes a matrix into two components: a low-rank structure representing the clean underlying patterns, and a sparse matrix capturing the outliers and corruption. The mathematical theory behind these robust approaches provides surprising guarantees. If the underlying matrix has a sufficiently low-rank structure, it can be recovered even when a significant fraction of entries are missing or corrupted. The Eckart-Young theorem provides the theoretical foundation for this capability, confirming that truncated SVD delivers the best possible low-rank approximation by minimizing the Frobenius norm of the error. Visual examples demonstrate the power of these techniques. Consider an image reconstruction task where 70% of pixels are randomly removed. A standard approach would simply interpolate between known pixels, producing a blurry approximation. In contrast, SVD-based matrix completion can recover the image with remarkable fidelity by identifying the underlying low-dimensional structure of the image data. The applications extend far beyond images. In scientific domains like genomics, measurement matrices often contain significant gaps due to failed experiments or resource constraints. SVD-based approaches can effectively impute these missing values by leveraging the correlations among genes across different conditions. Similarly, in sensor networks where individual sensors may fail intermittently, these techniques maintain accurate monitoring by recovering the missing readings. What makes these approaches particularly valuable is their ability to adapt to different noise profiles. When dealing with Gaussian noise that affects all measurements equally, truncated SVD naturally filters out the noise by capturing only the dominant patterns associated with the largest singular values. For structured corruption, where specific entries are severely affected, robust PCA approaches can isolate and remove these outliers without compromising the recovery of the underlying patterns. Experimental comparisons between standard SVD and its robust variants show dramatic differences in performance on corrupted datasets. While standard SVD's reconstruction error increases linearly with corruption levels, robust variants maintain stable performance even with 30 to 40% of entries corrupted. This resilience makes them invaluable in applications where data quality cannot be guaranteed. From handling corrupted data to predicting human preferences, SVD's versatility reaches far beyond academic exercises. When Netflix launched their $1 million prize in 2006, they weren't just looking for better movie recommendations, they were challenging the world to solve what might be the ultimate matrix completion problem. The Netflix prize competition became a watershed moment in recommender system development. With $1 million on the line, the contest attracted thousands of teams worldwide competing to improve Netflix's existing recommendation algorithm by just 10%. What made this challenge particularly fascinating was the scale and sparsity of the problem. Netflix provided contestants with a massive user item matrix containing over 100 million ratings, but the average user had rated less than 1% of the available movies. This extreme sparsity created a perfect testing ground for matrix completion techniques. Traditional recommendation approaches struggled with such incomplete data, but SVD-based methods proved remarkably effective. The mathematical challenge boiled down to a fundamental question: could the underlying patterns in user preferences be captured in a low-dimensional representation? Collaborative filtering emerged as the dominant strategy, with matrix factorization at its core. The approach works by simultaneously discovering latent factors for both users and items. Imagine decomposing the enormous user movie rating matrix into two much smaller matrices, one representing users in terms of latent preferences, and another representing movies in terms of latent characteristics. What makes these latent factors particularly powerful is their interpretability in the recommendation context. Though mathematically derived, they often correspond to meaningful features. In movie recommendations, these factors might represent concepts like preference for action sequences, sensitivity to dialogue quality, or appreciation of visual aesthetics. Dimensions that aren't explicitly labeled but emerge naturally from the patterns in user ratings. The winning approaches in the Netflix prize all leverage variants of matrix factorization, with SVD playing a central role. By approximating the original sparse rating matrix with a product of lower dimensional matrices, these algorithms could effectively predict how users would rate movies they hadn't yet seen. The key insight was that users with similar patterns across even a small subset of commonly rated movies would likely have similar preferences for other films. The mathematical elegance of this approach lies in how it transforms an impossibly sparse problem into a tractable one. Rather than trying to directly model the relationship between each user and each movie, which would require complete data, SVD-based approaches model each user and movie in terms of their positions in a lower dimensional preference space. This compression captures the essential structure while filtering out noise and enabling predictions for the vast majority of user-movie pairs that lack explicit ratings. Performance metrics from the competition revealed just how effective these approaches could be. Teams progressively improved prediction accuracy by refining their SVD implementations and combining them with other techniques. The final winning solution, a blend of hundreds of predictive models with SVD variants at their core, achieved the target 10% improvement over Netflix's baseline algorithm. What's particularly interesting is how the competition accelerated innovation in the field. Teams discovered that incorporating temporal dynamics, how user preferences evolve over time, significantly improved prediction accuracy. They also found that ensemble methods combining multiple SVD-based models with different parameters often outperformed any single approach. The impact of the Netflix prize extended far beyond a single streaming platform. Today, virtually every major digital service incorporates similar recommendation techniques. E-commerce giants like Amazon use matrix factorization to suggest products based on browsing and purchase history. Music streaming services deploy these algorithms to create personalized playlists. Social media platforms leverage the same mathematical principles to determine which content appears in your feed. What makes SVD so universal in these applications is its ability to extract meaningful patterns from extremely sparse interaction data. Whether users are rating movies, clicking on products, or engaging with content, their behavior creates a sparse matrix of interactions that SVD can transform into actionable insights. The same mathematical foundation that allows Netflix to recommend your next favorite show enables countless other personalized digital experiences. The same mathematical principles that power Netflix's recommendation algorithm perform what seems like visual magic in the world of images. When we represent visual data as matrices, we create enormous structures. A single photograph can contain millions of individual pixel values. This is where SVD reveals its transformative potential by uncovering the hidden, low-dimensional structure within these pixel matrices. Images are naturally represented as matrices, grayscale images as 2D arrays of intensity values, and color images as 3 separate channels forming a 3D tensor. This representation makes them perfect candidates for SVD, which excels at finding patterns in matrix data. But working with these representations presents significant challenges. Storage requirements balloon quickly, processing becomes computationally intensive, and extracting meaningful features from raw pixels seems nearly impossible without sophisticated techniques. When applied to image compression, SVD works by truncating the singular values to achieve various compression levels. The beauty of this approach lies in its adaptability. By retaining different numbers of singular values, we can create a spectrum of compressed versions. Each additional singular value we keep improves the visual quality, with the most significant improvements coming from the first few components. A 512x512 image can be dramatically reduced in size while maintaining remarkably good perceptual quality, all by keeping just a fraction of the original singular values. The process works because images contain significant redundancy and structure. The largest singular values capture the dominant visual patterns, broad shapes, major contrasts, and primary features, while smaller values often represent fine details and, eventually, noise. This creates a natural ordering of visual information from most to least important. This same property makes SVD extraordinarily effective for image denoising. When random noise corrupts an image, it distributes across all singular values rather than concentrating in the largest ones. By applying truncated SVD, we can effectively filter out this noise while preserving the essential structure of the image. The technique works by decomposing the noisy image, discarding the smaller singular values likely to represent noise, and reconstructing the image using only the larger values that capture meaningful features. The result is a cleaner image that retains its important visual characteristics. Perhaps most fascinating is SVD's role in facial recognition through the eigenfaces approach. In this application, a dataset of facial images is decomposed to extract the principal components, the eigenfaces, which represent the core variations across the entire face dataset. These eigenfaces aren't typically recognizable as specific individuals, but rather capture fundamental facial features and variations. The genius of this method is that any face can be represented as a weighted combination of these eigenfaces. By projecting new faces onto this eigenface space and comparing the resulting weights, we can determine similarity between faces with remarkable accuracy. This approach reduces the dimensionality from thousands of pixel values to perhaps just 100 eigenface coefficients, making facial recognition computationally feasible even for large databases. What makes SVD particularly valuable in computer vision is its ability to extract meaningful visual features automatically. The singular vectors reveal the directions of maximum variance in the image data, essentially identifying the most distinguishing visual characteristics without requiring manual feature engineering. These extracted features can then be used for classification, clustering, or other machine learning tasks. Performance comparisons consistently show that SVD-based approaches achieve comparable or superior results to specialized techniques, particularly for tasks like image compression and denoising. The decomposition reveals the underlying structure of image data so effectively that it facilitates better analysis across a wide range of computer vision applications. What's truly remarkable about these applications is that they all stem from the same mathematical foundation. Whether we're compressing an image to save storage space, removing noise from a medical scan, or determining whose face appears in a security photo, we're applying the same core technique, just in different contexts and with different parameters. The elegant mathematics of SVD works beautifully on moderately sized problems, but when faced with today's massive datasets, even this powerful technique hits a computational wall. What if I told you that by deliberately introducing randomness and probability into the equation, we could accelerate SVD calculations by up to 100 times while maintaining nearly identical results? The computational demands of traditional SVD become overwhelming when matrices grow to billions or trillions of elements. Consider genomics datasets with millions of genes across thousands of samples, or recommendation systems tracking billions of user interactions. Classical SVD implementations require operations proportional to the matrix dimensions, quickly becoming impractical at these scales. A matrix with just 1 million rows and columns would consume terabytes of memory and require weeks of processing time on high-performance systems. This computational barrier has spawned a revolutionary approach: randomized SVD algorithms. These methods cleverly approximate the exact solution by introducing controlled randomness. Instead of processing the entire matrix, they create a compressed version of the original problem through random sampling. The key insight is that we don't need perfect precision for most applications. We need a solution that's good enough with quantifiable error bounds. The randomized approach works by projecting the original matrix onto a lower dimensional subspace using a random matrix. This creates a much smaller problem that can be solved efficiently while still capturing the essential structure of the data. What makes this technique particularly powerful is that it comes with probabilistic error guarantees. We can be mathematically confident that our approximation will be close to the exact solution with high probability. The efficiency gains are truly impressive. When dealing with tall matrices, those with far more rows than columns, randomized SVD cuts the computational complexity from O mn2 to roughly O mn log 1e plus n3, where e indicates how accurate you want the result to be. In other words, computations that once took days can now be done in minutes or hours, all without compromising the quality needed for later machine learning tasks. For matrices too large to fit into memory entirely, the method of snapshots offers an elegant solution. This technique processes the data in manageable chunks by loading only a few columns at a time. Instead of working with the full matrix, it computes inner products between columns to build a correlation matrix, then performs eigendecomposition on this smaller matrix. This approach is particularly valuable in fields like fluid dynamics or when processing massive sensor arrays where storing the complete dataset in memory is impossible. The memory efficiency of randomized SVD is equally impressive. Traditional algorithms require storing multiple copies of the original matrix during computation. In contrast, randomized approaches often need only a small sketch of the matrix, dramatically reducing memory requirements from terabytes to gigabytes for large-scale problems. This reduction makes SVD feasible on standard computing hardware for problems that previously demanded specialized high-performance systems. For truly enormous datasets, distributed computing frameworks extend these capabilities further. Modern implementations distribute SVD computations across multiple machines in a cluster, dividing the workload and leveraging parallel processing. Cloud computing platforms now offer specialized libraries that automatically handle this distribution, making large-scale SVD accessible to data scientists without expertise in distributed systems. A genomics analysis that might take weeks on a single machine can be distributed across hundreds of nodes and completed in hours. These advances have transformed what's possible in large-scale machine learning. Image recognition systems can now process billions of images to extract visual patterns. Recommendation engines can analyze the entire history of user interactions across massive platforms. Natural language processing models can discover semantic relationships across the entire internet corpus. Problems that were previously deemed computationally infeasible are now routine. The beauty of these approaches lies in their practical balance between mathematical rigor and computational pragmatism. While traditional SVD guarantees exact results, randomized methods provide controlled approximations with quantifiable error bounds, a reasonable trade-off given the massive performance improvements. For most real-world applications, the difference in results is negligible, while the gain in computational efficiency is transformative. There's an unexpected revelation hiding at the intersection of classical linear algebra and modern deep learning. Despite the perception that neural networks represent a fundamental departure from traditional machine learning approaches, the mathematical principles of SVD continue to silently influence how deep learning systems operate and perform. At first glance, neural networks and SVD appear to be distant relatives in the machine learning family. Neural networks build complex, nonlinear representations through layers of interconnected nodes, while SVD offers a clean, interpretable matrix decomposition. One seems to embrace complexity, while the other strives for mathematical elegance. But this supposed dichotomy breaks down when we examine the mathematical foundations more closely. The first surprising connection emerges in neural network initialization. When we set up a neural network, the initial values of weights critically impact training dynamics and convergence. By applying SVD-based initialization, we can structure these starting weights based on the singular values of the data matrix. This approach provides networks with a more informed starting point that reflects the underlying data structure, often leading to faster convergence during training. Rather than random initialization, SVD offers a principled way to begin the learning process with weights that already capture some essence of the data distribution. Even more fascinating is how certain neural network architectures implicitly perform operations remarkably similar to SVD. Consider the humble autoencoder, a neural network designed to compress data into a lower dimensional representation before reconstructing it. Though constructed as a neural network with nonlinear activation functions, when these autoencoders use linear activation functions in their hidden layers, they effectively learn the same subspace as PCA and, by extension, SVD. The network naturally discovers directions of maximum variance just as SVD identifies the principal components. This revelation suggests that neural networks may sometimes be reinventing the mathematical wheel, arriving at solutions that classical linear algebra had already formalized decades earlier. The relationship extends beyond theoretical connections to practical applications. For instance, after training a neural network to high accuracy, the resulting model often contains redundant information across its weight matrices. This redundancy presents an opportunity for compression. By applying SVD to these weight matrices, we can approximate them with lower rank representations, significantly reducing the model size while maintaining performance. A neural network with millions of parameters might retain nearly identical accuracy with just a fraction of its original size after SVD-based compression, a crucial advantage for deploying models on resource-constrained devices. SVD also offers a window into neural network interpretability, one of the most challenging aspects of deep learning. By decomposing the weight matrices of trained networks using SVD, researchers can analyze the contribution of different features to the model's predictions. The singular values and vectors reveal the underlying structure of the learned representations, making it possible to understand which directions in the input space most strongly influence the network's decisions. This connection transforms SVD from a mere computational tool into an analytical lens that helps demystify the often opaque inner workings of neural networks. The implications of these connections extend far beyond academic interest. By recognizing how SVD relates to deep learning, we can design better neural network architectures that leverage these mathematical principles explicitly rather than rediscovering them implicitly through gradient descent. Networks initialized with SVD-informed weights typically converge faster and generalize better. Compression techniques based on SVD enable deployment of powerful models in memory-constrained environments like mobile devices, and interpretability methods drawing on SVD concepts help address the black box problem that has long haunted deep learning applications in critical domains. Consider a practical example. In computer vision, convolutional neural networks, CNNs, process images through layers of filters that detect increasingly complex patterns. These filter weights, when analyzed through SVD, often reveal that only a small number of directions capture most of the relevant visual information. By explicitly designing networks to focus on these directions, we can create more efficient architectures that require less computation while maintaining high accuracy. The mathematical insights from decades-old matrix factorization techniques continue to guide cutting-edge neural network design. When Netflix faced the daunting challenge of improving their recommendation system, they didn't just need a better algorithm, they needed a comprehensive machine learning pipeline capable of processing millions of sparse user ratings. This real-world problem perfectly illustrates how SVD serves as a critical bridge in production systems handling massive high-dimensional datasets. The Netflix Prize competition presented unique challenges that mirror those in many modern machine learning applications. The user item matrix was extremely large, potentially containing hundreds of millions of entries, with most values missing. Engineers needed to transform this sparse, high-dimensional data into a form that could power accurate predictions while maintaining computational efficiency. Let's examine how SVD would be integrated into such a complete machine learning pipeline. The process begins with data collection and pre-processing. For the Netflix dataset, this involved gathering user ratings across thousands of movies, cleaning outliers, and preparing the sparse matrix. A critical decision at this stage is how to handle missing values. Should they be imputed with averages, zeros, or left as unknowns for specialized algorithms? Once the data is prepared, SVD enters the pipeline at a strategic position. In Python, implementing SVD for this application might look like Python from Sclern decomposition import truncated SVD from Sclern.pipeline import pipeline soccer create pipeline with SVD and downstream model SVD truncated SVD in components 100 pipeline pipeline SVD regression model train pipeline on available ratings, pipeline.fit sparse ratings and matrix. This code illustrates how SVD is positioned between raw data and the predictive model, acting as a dimension-reducing transformer that extracts latent factors. For the Netflix dataset, these factors represent underlying patterns in user preferences and movie characteristics. The method of snapshots becomes particularly valuable when datasets cannot fit into memory. This approach allows for processing the data in smaller chunks, enabling extraction of patterns without requiring the entire dataset to be loaded simultaneously. In the Netflix Prize context, this meant teams could work with the massive dataset without requiring supercomputer resources. The integration of SVD results with downstream models creates a powerful system. The decomposed matrices, U containing user preferences, sigma containing importance weights, and V/T containing movie characteristics feed directly into prediction algorithms. These compressed representations capture essential patterns while eliminating noise, improving both computational efficiency and prediction accuracy. The SVD parameters chosen have system-wide impacts. In the Netflix Prize competition, teams discovered that the number of singular values retained dramatically affected both prediction quality and computation time. Too few components failed to capture important preference patterns, while too many introduced noise and computational overhead. The optimal range typically fell between 50-300 dimensions, a dramatic reduction from the original thousands of movies. Performance metrics from the Netflix Prize demonstrated that SVD-based approaches significantly improved recommendation accuracy compared to traditional methods. Teams leveraged SVD to effectively manage the sparsity of the user item matrix, enhancing their model's predictive power while keeping computational requirements manageable. Best practices for incorporating SVD into production pipelines include careful data preprocessing, normalization and scaling before applying SVD, and judicious selection of retained singular values based on the specific application. For collaborative filtering tasks like Netflix's, this often means balancing between compression efficiency and maintaining sufficient information for accurate predictions. The Netflix case study reveals general principles applicable across machine learning domains. First, dimensionality reduction should be positioned strategically in the pipeline after cleaning but before model training. Second, proper normalization is essential for meaningful decomposition. Third, the choice of dimensions to retain should be driven by empirical performance rather than arbitrary thresholds. This integrated approach doesn't just improve individual model accuracy, it transforms the entire machine learning workflow. By reducing dimensions early in the pipeline, all downstream operations benefit from improved efficiency. Training becomes faster, models require less memory, and inference speeds up significantly. The efficiency gains we've seen from SVD in production systems represent just the beginning of its evolutionary path. As data moves beyond traditional two-dimensional matrices into multidimensional tensors, an entirely new frontier of decomposition techniques is emerging that could reshape how we process complex data across disciplines. While SVD has established itself as a cornerstone of modern machine learning, today's increasingly complex data structures are pushing beyond its classical formulation. Consider neuroimaging data that combines spatial, temporal, and subject dimensions, or recommendation systems that track user preferences across products, time, and context. These multidimensional problems can't be adequately flattened into matrices without losing critical relational information. This is where tensor decompositions enter the picture, extending SVD's powerful concept to data with 3 or more dimensions. Unlike traditional matrices, tensors preserve the natural multidimensional structure of complex data. Fields like neuroscience and computer vision are particularly benefiting from this approach, as their data inherently exists in higher dimensions. Tensor methods allow researchers to analyze brain activity patterns across spatial regions, time points, and experimental conditions simultaneously, revealing insights that would be obscured when flattening the data. Meanwhile, at the computational frontier, quantum computing approaches to matrix factorization promise to revolutionize how we handle massive datasets. Current randomized SVD algorithms have already achieved impressive 20x speedups, but quantum implementations could potentially deliver exponential improvements. Quantum algorithms leverage fundamental properties like superposition and entanglement to process multiple possibilities simultaneously, potentially transforming computations that currently require hours into operations that complete in seconds. The implications for machine learning are profound. Imagine training complex models on data sets so large that current systems would require days to process them, completed instead in minutes through quantum-accelerated SVD. While practical quantum computing at scale remains on the horizon, early algorithmic work is already laying the foundation for this computational leap. Another significant development is the emergence of adaptive and online SVD algorithms designed for streaming data applications. Traditional SVD operates as a batch process on static datasets, but modern applications like social media monitoring, financial market analysis, and IoT sensor networks generate continuous data streams that require real-time processing. These adaptive algorithms allow SVD to be continuously updated as new data arrives, without recomputing the entire decomposition from scratch. For recommendation systems tracking user behavior, this means the ability to incorporate new interactions immediately into the model, creating more responsive and accurate suggestions. In sensor networks, online SVD can identify emerging patterns and anomalies in real time, enabling faster responses to changing conditions. Beyond algorithmic advances, SVD is being integrated with emerging computing paradigms like federated learning and edge computing. As data privacy concerns grow and regulations tighten, federated learning, which trains models across multiple devices while keeping data local, is becoming increasingly important. SVD plays a crucial role in this distributed environment by reducing the dimensionality of data that needs to be shared between devices, preserving privacy while maintaining model quality. In edge computing scenarios, where processing occurs on devices at the network's edge rather than in centralized data centers, SVD helps overcome the memory and computational constraints of these smaller devices. By reducing data dimensions, SVD enables sophisticated machine learning models to run efficiently on smartphones, sensors, and IoT devices without requiring constant cloud connectivity. Current limitations in SVD's computational complexity are being addressed through innovations in randomized algorithms. These methods significantly reduce computation time, particularly for very large datasets where traditional approaches become prohibitively expensive. By sampling the original matrix intelligently, these algorithms can approximate SVD solutions with controlled error bounds, achieving speedups of up to 20 times while maintaining accuracy levels suitable for most applications. These advances are expanding SVD's practical applications into domains that were previously infeasible due to computational constraints. From real-time video analysis to genomic sequencing, systems that once struggled with data volume can now process information efficiently through these optimized approaches. While these optimized approaches have democratized SVD across new domains, they've also introduced a dangerous paradox. The easier SVD becomes to implement, the more likely practitioners are to misunderstand its fundamental mechanics. Despite its widespread adoption, SVD's mathematical elegance often masks subtle complexities that trip up even seasoned data scientists. Perhaps the most persistent misconception revolves around the relationship between SVD and eigendecomposition. Many practitioners treat them as entirely separate techniques, when in reality SVD can be viewed as a generalization of eigendecomposition. Unlike eigendecomposition, which only works on square matrices, SVD provides a powerful framework applicable to any rectangular matrix, a critical distinction that expands its utility across diverse data structures. When implementing SVD in practice, the decision of whether to center your data becomes a frequent source of confusion. This seemingly minor pre-processing step can dramatically impact results. Centering is essential when analyzing variant structure, as it ensures the first singular vector captures the direction of maximum variance. Without proper centering, the decomposition may emphasize absolute magnitude rather than variance patterns, leading to misleading interpretations of your data's underlying structure. The interpretation of singular values presents another common pitfall. Many practitioners oversimplify by viewing singular values merely as indicators of importance, missing their true mathematical significance. Singular values represent scaling factors that quantify how much variance each singular vector captures. This nuanced understanding becomes crucial when deciding how many components to retain or when comparing the relative significance of different patterns in your data. Implementation errors frequently stem from misunderstanding matrix dimensions in SVD. When using economy SVD to improve computational efficiency, the resulting matrices U and V won't be square. This seemingly technical detail can cascade into errors throughout your analysis if you make incorrect assumptions about matrix properties in subsequent calculations. A frequently asked question is about the computational efficiency of SVD, especially for large-scale applications. While we've covered randomized approaches, many practitioners fail to leverage the specific structure of their problem to optimize performance. Understanding the mathematical properties of SVD can reveal opportunities for dramatic computational gains through specialized implementations, even without resorting to approximate methods. Another area ripe for confusion concerns the interpretation of left and right singular vectors. The left singular vectors from matrix U correspond to the original data's column space, while the right singular vectors from matrix 5 relate to the row space. This distinction becomes particularly important in applications like recommender systems, where these vectors represent fundamentally different entities with distinct interpretations. The applicability of SVD to non-square matrices represents a significant advantage that's often overlooked. Many data scientists incorrectly assume they need to transform their rectangular data into square matrices before applying matrix decomposition techniques. This misunderstanding stems from conflating SVD with eigendecomposition, leading to unnecessary pre-processing steps that can introduce bias or distortions. Many practitioners also neglect the importance of the Frobenius norm, when evaluating SVD approximation quality. This mathematical measure quantifies the error between your original matrix and its low-rank approximation, providing a rigorous framework for determining how many singular values to retain. Without this quantitative approach, decisions about dimensionality reduction become arbitrary rather than data-driven. These misconceptions highlight the critical importance of understanding the mathematical foundations of SVD rather than treating it as a black box algorithm. By recognizing these common pitfalls, you can implement SVD more effectively and extract deeper insights from your data. The time invested in developing this mathematical intuition pays dividends across virtually every machine learning application, from recommender systems to computer vision. What if the same mathematical technique that powers Netflix recommendations could also decode facial recognition patterns, compress satellite imagery, and extract meaning from millions of text documents without changing its fundamental structure? This remarkable versatility is precisely what makes Singular Value Decomposition the universal translator of machine learning. When we examine machine learning systems as interconnected networks rather than isolated algorithms, a critical challenge emerges. How do we enable different components to communicate effectively when they expect data in radically different formats? This is where SVD reveals its most profound value as a standardized mathematical protocol that bridges disparate data domains. At its core, SVD functions as a translation service, converting complex data structures into simplified forms that expose the essential patterns. Consider how SVD seamlessly transforms a sparse user item matrix in recommendation systems into dense, latent factors that capture user preferences and item characteristics. This same mathematical framework then extends effortlessly to image processing, where it extracts eigenfaces from pixel data, or to natural language processing, where it identifies semantic relationships between words. The true power of SVD lies in its ability to create interoperability between different machine learning techniques. By providing a standardized method for dimensionality reduction, SVD establishes a common language that diverse algorithms can understand. A clustering algorithm doesn't need to know that its input originally came from satellite imagery. It simply requires well-structured features that represent the underlying patterns, which is precisely what SVD delivers. This universal quality stems from SVD's mathematical foundation. By decomposing any matrix into three components that represent orthogonal patterns, scaling factors, and directions of variation, SVD creates a consistent framework for understanding structure regardless of the original domain. It's like having a translator who speaks every data dialect fluently. The Netflix prize competition provides a perfect illustration of SVD's translational capabilities. Teams needed to bridge the gap between sparse user ratings and predictive models. SVD served as the intermediary, transforming an incomplete user item matrix into a structured format that revealed underlying patterns of movie preferences. This same mathematical approach extends across domains, from genomics data to financial transactions to sensor networks, always maintaining its fundamental structure while adapting to the specific characteristics of each domain. SVD's role as a data translator becomes especially valuable when we consider how it enables communication between different stages of machine learning pipelines. Raw data enters the system in high-dimensional, often chaotic forms: pixels, text tokens, sensor readings. Models, however, require well-structured, informative features to perform effectively. SVD bridges this gap by capturing dominant correlations within data matrices, functioning as an intermediary that facilitates information flow between pipeline components. This translation capability extends beyond just data formatting. SVD also helps translate between human understanding and machine processing. By revealing the principal components of variation in complex datasets, SVD makes the underlying patterns interpretable to humans, while simultaneously preparing the data for algorithmic processing. Data scientists often describe SVD as a data-driven generalization of the Fourier transform, allowing for tailored transformations based on the specific problem at hand. While the Fourier transform decomposes signals into fixed sine and cosine components, SVD adaptively identifies the most relevant components for each dataset, enhancing its utility as a universal translator in data science. The ability to maintain mathematical consistency while adapting to diverse domains makes SVD indispensable in modern machine learning. As data volumes grow and applications diversify, this universal translation capability becomes even more valuable. Systems that can effectively communicate across domains, from computer vision to natural language processing to recommendation engines, will increasingly rely on techniques like SVD to establish the necessary bridges. By facilitating communication between different parts of the machine learning ecosystem, SVD doesn't just solve individual computational problems. It enables entire systems to function cohesively. This systemic perspective reveals why SVD remains fundamental despite decades of algorithmic innovation. It's not merely a mathematical technique, but a core communication protocol that allows disparate components to work together. The gap between knowing SVD's potential and actually harnessing it systematically might be smaller than you think. Behind every successful implementation lies not a complex framework, but a surprisingly straightforward checklist that addresses the connections between components rather than isolated optimizations. As we've explored SVD's mathematical foundations and diverse applications, you've gained theoretical understanding, but how do you transform this knowledge into practical results when facing real deadlines and resource limitations? Implementing SVD effectively requires a structured approach that begins with thoughtful data preprocessing. Before applying any decomposition, ensure your data is properly prepared by addressing missing values, scaling features appropriately, and considering whether centering is necessary for your specific application. This preliminary work significantly impacts SVD's effectiveness, but is often rushed in the face of project deadlines. Take the time to validate your pre-processing choices through small-scale experiments before proceeding to the full dataset. When computing SVD itself, the implementation method you choose should align with your dataset characteristics and computational constraints. For massive datasets that won't fit in memory, consider the method of snapshots, which allows you to compute SVD without loading the entire data matrix at once. This diagnostic approach processes data in manageable chunks, making previously impossible analyses feasible while preserving mathematical validity. Decision frameworks for parameter selection should extend beyond simplistic rules to consider system-wide implications. When determining how many singular values to retain, avoid treating this as an isolated mathematical decision. Instead, evaluate the computational cost of keeping different numbers of components against the impact on downstream model performance. While the elbow method provides a quick visual assessment of the singular value distribution, supplement this with quantitative metrics that measure the percentage of variance captured. Some applications may require preserving 99% of variance, while others perform optimally with just 80–90%. Integration of SVD results with downstream models requires careful consideration of data flows throughout your pipeline. Design your system to maintain consistency between training and inference paths, ensuring that any transformations applied during development are properly encoded for production deployment. This systems thinking perspective prevents the common pitfall of building components that work in isolation but fail to function cohesively. Diagnostic tools can help identify opportunities for SVD application in existing pipelines. Visualizing singular value distributions often reveals when dimensionality issues are limiting performance. A steep drop-off after the first few singular values indicates that most information is concentrated in a low-dimensional subspace, making SVD particularly beneficial. For large datasets, benchmarking different implementation approaches can demonstrate where computational bottlenecks occur and guide optimization efforts. Perhaps most importantly, recognize that SVD implementations should evolve along with your understanding of the problem domain. The optimal approach emerges through iteration rather than being determined entirely in advance. Start with simpler implementations and progressively refine based on performance metrics and computational profiling. This adaptive strategy balances immediate progress with long-term optimization. Resource-wise, you're not alone in this journey. Libraries like NumPy and SciPy provide efficient implementations of SVD, while scikit-learn offers specialized variants like truncated SVD for larger datasets. For advanced applications, randomized SVD algorithms can deliver dramatic speedups with minimal accuracy loss. The academic literature continues to yield valuable case studies demonstrating SVD applications across domains. Research papers from conferences like NeurIPS, ICML, and KDD frequently showcase innovative implementations worth studying. Before and after case studies consistently demonstrate significant improvements from applying SVD with a systems approach. Recommender systems have achieved performance gains while reducing computational requirements by identifying the optimal truncation threshold for their specific data characteristics. Image processing pipelines have benefited from properly tuned SVD implementations that preserve essential visual information while eliminating noise, but only when the entire pipeline is considered holistically. Small changes in how you approach SVD implementation often yield outsized benefits. Rather than viewing SVD as a standalone technique to optimize in isolation, position it as a communication protocol that enables different components of your machine learning system to work together effectively. This perspective shift from local optimization to system-level thinking transforms SVD from a mathematical curiosity into a practical tool for solving real-world problems with tangible impact. Throughout our journey, we've explored how SVD functions as a mathematical cornerstone that transforms raw data into meaningful insights. As computer scientist Richard Hamming wisely noted, "The purpose of computing is insight, not numbers." This encapsulates the systems thinking approach we've been advocating, where understanding relationships within data becomes more valuable than the individual data points themselves. The power of SVD becomes increasingly evident as data scales grow larger. What makes SVD exceptional isn't just its mathematical elegance, but its ability to serve as a communication bridge between various components of machine learning systems, allowing them to speak a common language of patterns and structures. Looking forward, as data complexity continues to grow, foundational techniques like SVD will evolve alongside emerging technologies, adapting to new challenges while maintaining their essential role in the data scientist's toolkit. By positioning SVD within a holistic systems framework, you're equipped to make more informed decisions about where and how to apply dimensionality reduction for maximum impact in your machine learning endeavors.